These are notes on the nature of gases, Chapter 13.1 and 14.1. Chapter 13 is states of matter, and the first section specifically deals with gases, and then Chapter 14 deals with gases. The entire chapter is gases, and so 14.1 is the first section of that. So first we're going to look at kinetic theory and gases specifically. So kinetic theory is the idea that all matter is made up of particles in constant motion. And you know this from your middle school days, where particles in a solid are moving less than particles in a liquid, which are moving less than particles in a gas. But regardless, all matter has particles in constant motion. And so in order to apply this to gases, we make certain assumptions about gases. And this is also known as kinetic molecular theory of gases. So the first assumption we make is that the particles that make up a gas, so these are specific to gases, not liquids or solids, that the particles are considered to have insignificant volume, and the motion of one particle has no effect on another particle. If you remember, the particles of gases are really far apart compared to solids and liquids, and so they don't affect each other when they're moving around. There's no attraction or repulsion. They're so far apart that gases are compressible. You can kind of push them together a little. Compare that to a solid. You know, if you have a chair, you can't really compress it. Even a liquid, you can't compress it, can't push it into a smaller volume. But gases you can, because there's so much room between gases that they don't affect each other. And so because of that, they're considered to have insignificant volume. Each particle, not a jar of gas altogether, but each particle is considered to have insignificant volume. But gas particles do have mass, so keep that in mind. So the second assumption we make about gases is that the motion of particles is rapid, so really fast, constant, they're constantly moving, linear, meaning they move in a straight line, and random. There's no reason for their movement. It's random. That said, if they hit something, then they're going to change direction. So you can almost think about this as if you're playing pool and you have the break, so you break the little triangle of all the pool balls, and they go in random motions until they hit something, and then they change direction. But that motion is rapid, constant, linear, in a straight line, and random. And this is also why gases fill to fit their container. So if you pour liquid into a glass, it stays at the bottom of the glass. But the gases, if you have, say, a closed jar, are going to fit the container. Another way of saying this is, if you spill water in the corner, that water stays in the corner. But if somebody, say, opens an orange, slowly those orange gas particles fill to fit the room and everybody smells the orange. That's why that happens. And then finally, the third assumption we make is all collisions between particles are completely elastic. So there's no energy lost. Again, consider pool balls. Energy may be transferred between particles, but there's no actual energy lost in these collisions between gas particles. So that's kinetic molecular theory, and those are kind of the assumptions we make about gases. So now let's look at an overview of what measurements we're going to make regarding gases. So some of these are going to be familiar, some of these are going to be new. So we'll start with some new things. The first measurement we make, or not the first, but one measurement we make is pressure. And we denote pressure with a capital P. So if you see the variable capital P, that means pressure. And that's the result of the collision of billions of rapidly moving gas particles with an object. So if you're talking about the pressure of a gas in a container, it's the pressure of the gas of those particles hitting the sides of the container. A balloon stays filled up because of the pressure of the gas inside. And that's because all of these rapidly moving particles, billions of them, are hitting the sides of the balloon. One particle itself isn't going to exert much pressure, but all of these particles moving together are going to exert pressure. And the units we're going to use, there's a couple. We often use the kilopascal, that's kPa, the atmosphere, which I think we've heard of earlier in this year, millimeters of mercury, Hg being the symbol of mercury. And so the conversions between these are 1 atmosphere equals 101.3 kilopascals, or 760 millimeters of mercury. The next one is temperature, so that we designate with a capital T. And temperature is proportional to the average kinetic energy, which kinetic energy, if you remember from your physical science days, is 1/2 mass times velocity squared, or your physics days if you've already taken physics. So temperature is proportional to the average kinetic energy of the particles. Notice we're talking about average because any one particle may have slightly more energy than another particle. And we're also talking about the average kinetic energy, not the average velocity. So what that means is if you have two containers of gas, let's say a container of argon gas and a container of helium gas, argon has a lot more mass than helium. So at the same temperature, the helium gas is actually going to be moving faster, have a higher velocity because it has a lower mass. So just because particles of one thing are moving faster than particles of another gas doesn't mean they have a higher temperature. Now, if you have particles of the same gas and one is moving faster, then it would have a higher temperature because they have the same mass. But keep that in mind, that temperature is proportional to kinetic energy, not to velocity alone. And the unit we usually use is the Kelvin. And 1 Kelvin, so to convert between Celsius and Kelvin, see, I'm going to move that up here. To convert between the two, it's the temperature in Kelvin equals the temperature in Celsius plus 273.15. So it's just an easy conversion. A unit of Celsius equals a unit of Kelvin, so there's no multiplication factor like there is between Celsius and Fahrenheit. We also measure the amount of gas, which is designated with a lowercase n, and that's measured in moles. So the more moles of gas we have, the more gas we have. It's pretty self-explanatory. We measure the volume of gas, and we measure, and that's designated with a capital V, and the unit for that is liters. And just remember that gases are going to expand to fill their volume. So that pretty much takes care of our ideas about measurement of gas and the kinetic molecular theory of gases. Please put any questions you have on YouTube or ask them tomorrow in class. Have a good day.